Let's try to distinguish your voice. Name.
Yeah.
Now I know you are.
I see.
Yes, I know this is yours. You have two,
Yes.
right?
Yeah.
And Jacob.
Thank you.
Yeah. Good job. I think it's the first time to do the homework. Okay.
We did a different question.
Yeah, but that you did correct. That's all. That's
You
it.
wish to check this one?
Oh, I didn't.
This is all.
Ah, you already finished the homework too. Okay. All right. I'm going to grade you. You did good job. Yours. Oh, okay. I saw the number is question one, so okay. Good. Yeah, I will do that. Okay. Thank you.
Where do you find the time?
Yeah.
Yeah, wait.
When I said to
You
do
didn't
homework.
sleep last night? Oh, the day before.
Yeah.
Uh,
I said just two questions and I.
okay, yeah, just two. So
Yeah.
Man,
So when
he already, I'm like already regretting sleeping last night. I'm like, did I make the wrong call?
you already know everything. So actually, this course we have already studied in Nepal.
ah, similar.
Yeah,
Oh, that's good.
he did very well.
Yeah.
4 out of 5.
Okay.
So he is very big.
So let's start it. I will look at it out of it. You think,
Right information. Actually, all the courses that here we should consider food course, we have already studied in Nepal. Theoretical mechanics, quantum mechanics, first and
Yeah,
second,
yeah.
And
That is, you mean undergraduate or graduate?
graduate.
Okay, you have already graduate
Yeah.
degree in there,
Yeah,
so
yeah.
yeah, that is good, good. So for semi-holonomic, last time I think we reached here, if there is a holonomic such that this non-holonomic constant is just total time duty for this, then we say that is semi-holonomic. Say so it is specification with this. So now we're going to prove all the boundary condition. Condition for this, right? So let's this is all we require, right? And then let's first look if this one is dfr dt and g is a function of qg and qg dot. So when we do the total time duty, I'm going to use a k here. K from 1 to n r shift f r shift qg as k. Okay. Okay. Did you use the same textbook in Nepal?
Textbook?
Textbook,
Goldstein.
the same,
Yeah,
right?
yeah.
Oh, okay.
But
But,
different edition. Edition very different.
that time maybe just first edition, right?
Yeah,
Or
yeah.
almost the same. Okay, and this one, and the second one is partial T, right? And so now we want to see, okay, let's look this one. We introduce the mixture element and see if that happen for semi-holonomic, what this term will be, right? So now let's look at first is partial GR, partial PR, let's use QG dot, okay. QG dot. Is this term? So G alpha is here, then we have a K1 in partial. Okay. Partial, because this function does not depend on the generalized velocity, so we keep here. And this one, when only k to j, so we have this one, right? So then this one does not depend on the, because f does not depend on this general velocity, so that is only when only K produce this summation disappear. And the second one is the partial G, so here let's do this term. Here inside this is again a function of Qj, so we have second order derivative. J. And this one does not belong, so this is still keep it. Then we go to this one, right? So this one is also the second order derivative, partial P, partial J. Now we look this one, right? So now the total term derivative of partial Qg is partial G alpha partial Q J alpha is we're going to do this term for total term derivative, this term. So this term we have summation, right? Because this one is function of if I use K from 1 to n, then the partial second order derivative of partial Q J, partial Q K, and Q K dot. Right, and then we have also the partial second order partial Q, partial Q J. So then let's look this G alpha J. G alpha J is this term, right? This term subtract this term. And you see these two terms are cancelled, right? So we have 0 for all the J from 1 to n, alpha from 1 to n. So all the matrix elements, if not all matrix elements of G alpha J equal to 0, then, okay, because we assume this already satisfied semicolon. So if G has this relation, then we have to find the matrix element capital G alpha J is 0. So next time, when we have this non-polynomial constraint, equation constraint, if it is linear, of course, if not linear, we will not go further. If linear, you just check this one. So this is a condition to double check whether this non-polynomial constraint is semi-polynomial. Okay, that is proof. Okay, and there's other way. Alternately, you can also try to find other ways. So I will skip this part. Now, once we have this, then we'll come back to here. So this is the second case if for the non-polynomial constraint with linear in the general velocity. The Lagrange or general Lagrange equation is this one. Left hand side, same thing. The right hand side have two terms. But now for the semi-hollow, this term disappeared, right? So for now for this one, the Lagrange equation or general Lagrange equation is reduced to G equal to minus, right? Alpha from 1 to m. Here, mu alpha dot partial Qg, partial G alpha partial Qg dot is this one. Here, textbook made mistake, they miss this negative sign. They miss is mu alpha dot, they just say mu alpha. And this must be G alpha, not F alpha, because we want to distinguish F alpha will also is holonomic, and the non-holonomic we usually use G alpha. So that is the correct formula. Okay, and now let's consider in general number 3. So this is for only has a holonomic. We are going to apply this formula here. We introduce this undeterminate Lagrange undetermined multiplier lambda, which is a constant, and f alpha, which is a holonomic, only function of general coordinates and time. But second case, if this constant is not holonomic but with a linear in the general velocity, we have this general Lagrange equation, which in regular set we have two terms. But if this non-holonomic constant is semi-holonomic, then we double check this condition. If that's satisfied that it's semi-holonomic, the general Lagrange equations come to here. Now, let's consider if we have case both holonomic and semi-holonomic together, or not, yeah, that's it. For holonomic and semi. So this case, and we have alpha, we have G alpha, and we have also, since we already said this, this semi-holonomic, I'm going to give this condition here also 0. So that is satisfied. When we have this and this, and also this G alpha, J is 0, then the generalize the Lagrange equation for this system is this textbook does not have this term, so I just give you. Actually, you can derive yourself and just combine. Okay, so here maybe I'm going to use to distinguish different index of alpha from 1 to m, and alpha prime from 1 to m prime, suppose, right? So alpha from 1 to m is lambda alpha, partial f alpha, partial qg, is this term, and plus I can minus because we have negative sign here, negative sign. So the minus alpha prime from 1 to m prime, mu alpha prime dot partial g alpha prime partial q g dot partial g alpha prime. Okay, so this is in case, and we are going to discuss one example about this. Okay. Now number 4. That is for holonomic and non-holonomic is Q. It's linear in Q, right? That is come back to this case. This case is if we have a non-holonomic, but not a semi-holonomic, so we have this term, because this term is non-zero. But now we also include holonomic. So this is a more general case. The Lagrange equation, the right-hand side, we have actually 3 terms, right? So now let's write down here and just summarize. So when we reach to any case, we first analyze the type of the constraint, then we are going to check which one is a formula we are going to use. G minus alpha prime from 1 to 1, mu alpha prime dot partial G alpha prime partial Okay, so that is a summary, and now let's go to some examples. I'm going to do 2 examples. One textbook has already discussed, so I will just skip that one. Example 1. Example 1 is one of textbook, but it is wrong, so I want to go slow and get you to correct that. So, okay, give us the Check G alpha. Okay. So see if it is semi-harmonic. So that is the first job. And then set up those equations of motion. So that is the after two, right? So now G alpha is give us is x dot y squared plus x y dot plus k z equal to 0. So alpha only to 1, right? Only one equation of constraint. And here what we know is there are two information. Lagrangian, so here's the Lagrangian. This is general kinetic energy plus potential energy. Minus V is, this is only single particle. X dot squared plus y dot squared plus V dot squared minus V. V is only function of position. Okay, so that is what we know and ask a question, right? So now, let's do this. First, let's check, right? So the check whether it is a semi-harmonic, we're going to check this one. Okay, so now let's do that. G alpha G is d dt partial G lower G alpha partial Q G dot minus partial G alpha partial Q G, right? So how many? We have Q1 equal to X. We have three general coordinates, right? X, Y, Z. So let's consider G alpha 1. Alpha is 1, right? Fine, you just as an index. So now G equal to 1, so that is d dt partial G alpha partial X dot minus partial G alpha partial X equal to, now let's see. Here, partial X dot we have a y squared, right? D dt y squared, right? This term. No x dot here, this partial x, this term, that is plus y dot. And that equal to 2y dot plus y dot not equal to 0. But text will say 0, so that is wrong. I do not know how they say that's 0. So that is the first time we check, okay. You may stop here because we need all to be equal to 0. One of them is not 0, but let's do others. I think we just do the exercise term. G alpha 2 is d dt partial G alpha partial y dot minus partial G alpha partial y. Now let's see. Partial y dot is this one, right? So that is x. And then partial y here, right? I think this is minus, right? Sorry, that is a minus. Because here it's minus, right? Okay, and this is minus partial G alpha partial y. This term we have is 2y x dot. Again, this is a x dot minus 2y x dot is not equal to 0. Okay, let's check 3. Z. G alpha 3 is d dt partial G alpha partial Z dot minus partial G alpha partial Z, which is d dt. Do we have a G dot? There's no, right? No Z dot. Partial Z is minus k. So that equal to minus k, right, because 0, so that is also not 0. So if it is not semi-hollow, this is sometimes given us this constraint, so we need to double check first. But after check, then we can see which equation we are going to use, right? So now this is the first one we check. Then now we go to next one is we are going to solve the equation motion. Just set up. We will not solve because that is the main part is mathematics, right? So now let's we have a g alpha. Okay, I think that's enough. Now let's go to which equation we are going to select. We have only one constraint. This constraint is non-holonomic, linear in the velocity. So that is this one, right? It's here. We have two terms. So okay, I can use this one. So now that is the first one. I go to second. Let's look because L, right? So now let's first, I mean, okay, just write down the equation. So now we are going to solve the equation of generalized Lagrange. Minus alpha, but here alpha equal to only 1, right? So that is the mu alpha dot partial g out partial q g out minus mu alpha g alpha g. Okay, now I can erase those. So here we have Lagrangian. So now we are going to do is for q1 equal to x, we have partial L partial x is only minus partial v partial x, right? Since it's only potential as a function of x, and the kinetic energy does not depend on the x, right? And then the partial L partial x dot is then x dot, right? Potential does not depend. Okay, so now this side we can have then we have d dt, so that is mx dot minus here, then plus, right? Partial v partial x equal to minus mu alpha dot is only one term. Then partial g alpha partial q g. I think I already did it, right? The first step, right? And this one. That is y squared. Y squared and minus mu alpha g alpha is this one. This step, right? We have a 2y x dot, right? Y dot, okay, 2y dot. So that is 2y minus 1 y dot. Yes. So that is equation 1, if you want to. That is equation 1 for the from this general Lagrange equation. We set up equation motion, and how to solve that. Of course, this one we can simply write here. The right hand side is mx double dot plus partial x. That equal to minus mu alpha dot plus minus mu alpha 2y minus 1 y dot. So this is equation 1. So now we go to second one. Q2 equal to 1. Partial L partial y is again partial minus partial v partial y. Right? Partial L partial y dot. Here is my dot. And then we can have d dt and y dot. Okay, and that is the minus became plus partial v partial y equal to minus v dot. And then the second one is this one. So partial T y partial T alpha partial y dot is x. So we have x and minus mu alpha G alpha 2 is that one is 2x, 1 minus 2y x dot. So then we have m y double dot plus partial v partial y equal to minus mu alpha dot x minus mu alpha 1 minus 2y x dot. That is equation 2. Last one, Q3 equal to z. We also do each individual term. Partial L partial z is minus k, right? Sorry, is partial minus partial. That is potential. Oh, okay, here. We have also okay. The potential partial L partial z dot is mz dot. Then we can have this Lagrange equation is partial L partial z dot partial L partial z equal to here we have I just immediately write down here. I do not need it. Mz dot dot plus partial v partial z equal to minus mu alpha dot, and then partial G alpha partial z squared is 0, right? So that is 0 and minus mu alpha, and then the G alpha 3 is minus k, right? So that is equation 3. Then the remaining part to solve this, you can see here, this equation has x and also has y. This equation has y and x, so they cross. It's not easy to direct, or these equations are not independent of each other. Now, that is the reason why I want to go this is try to play how to prove whether it is semi-holonomic or non-holonomic. The other is a textbook something wrong, so I want to make a correction. Second one, the textbook have this one. There is a rolling loop going down to the inclined surface, so I will not go through that. You can go through yourself and look at the textbook. Now I want to go to another example, which he is not here. He bring this one, right? So now I'm going to work on this, because this one is this case, -3 case.
I think he is preparing for math test.
Okay, yeah.
Yeah.
That is his question, and I'm prepared for him. But that's fine.
Well,
Yeah.
You can,
it.
yeah, he can look this video.
We have test right after this class.
It's very stressful.
Yes, I know that is the first exam, right? You
Yeah.
do not know what
Well,
kind. And
yeah.
it's a closed textbook?
Yeah, close.
I mean, the only reason it's stressful is because, we did qualifiers and just all the time for, studying, taken up by homework and then, I mean, we'll do our best.
Yeah, do your best. Okay.
Okay.
So this example here. I think because this make it bigger since it's the middle of this box, or otherwise you will see the holes. Okay, so now we have R, we have M1 and M2. Now let's give the condition. So that is the condition, for example, poly. Poly, it is direction-based. Now here, this is his question. So now I want to emphasize. When say the the Purdy's birthplace is on the beer, or at beer, not at this surface. It's here. This birthplace at. Okay, and also rotation without sleeping. Otherwise, the roof with this surface. Otherwise, you cannot rotate. That is also his second question. Without rotation. I also give a mass, so I have no space here to mass here. Capital M is the mass of this poly. So that is the first one. Second one about M1 is the surface is also fraction limits between M1 and surface or the cable, right? So that is the second condition. M1 and M2. Let's see this. Just write this. Roof. M1 and M2. So the length is the length L and the mass weight. So we do not consider the motion of roof. Mass. Okay, those are conditions. So now, the question is find the motion. The motion of M1, M2, and the support. Second, force due to the constraint. We have several constraints. So we are going to analyze. That is advantage of this extending Hamilton's principle. So now it's flat. Okay, we first do the analysis. Analyze the constraint in this case. Okay. The first constraint. Now I'm going to set up this coordinates so that we can select this general constraint. I'm going to set the axis here. X, Y. So I'm going to say